So this video is on linear programming or optimization. We call it linear because there is a thing called the objective function, and that is linear, and we have something called a constraint, and the constraints are also linear. So put them together, we call it linear programming. So what is this objective and what are the constraints? Well, in life, we could usually have some sort of a goal, and if there is potential in reaching that goal, one would want to maximize that potential. And if there are risks associated with that particular goal, then we want to minimize the risk that is involved. So the goal that we can define is what we call the objective function. Keep in mind that objective function has to be linear, so ax plus by, and the constraint that we impose mathematically should also be linear. If they're not linear, then we have another field called nonlinear programming, which we will not do here. So we either want to maximize the objective, which is the goal, or we want to minimize the objective. So what we need is an objective function, and we want to subject it to a set of constraints. In other words, we are going to work within the limitations that we have to either maximize or minimize the objective, which is our goal, and we mathematically represent it as a line. So when we have a system of inequalities and we graph it, we know we are going to get a set of solutions, and we would have an overlapping region. And that overlapping region is what we call the feasible region when it comes to linear programming. And we have something called the vertices or the corner points, and these are all feasible because of the constraints that we impose. And when we have the corner points, we have to evaluate the objective function at those corner points and see which corner point gives the maximum value if we want to maximize the objective, or which corner point gives us the minimum value if we are intending to minimize the objective. And then we would have a solution. So here is the first example, and this example is straightforward in the sense we have a feasible region. How did they get this feasible region? They actually used a set of constraints, and by using those constraints we came up with this feasible region. And we have a bunch of corner points here. So I'll write it as xy coordinates, and z equals 5x plus 6y is the objective function. So when x is 1, y is 2, x is 2, y is 10, x is 7, y is 5, x is 8, y is 3. And those would be the 4 points that we have. So I'm going to evaluate the objective function in each of those points. So in the first one, it should be 5 times 1 plus 6 times 2, which is 17. The next would be 5 times 2 plus 6 times 10, which would be 70, and 5 times 7 plus 6 times 5, which is 65. Excuse me. 5 times 8 plus 6 times 3, which would be 58. So the objective function is maximized with a value of 70 at that coordinate or corner point, and it is minimized. In other words, the lowest value happens at that coordinate, that particular case where the objective function is 17, and that would be the corresponding minimum corner point. So the maximum occurs for x is equal to 2 and y equals 10, and the minimum occurs for x is equal to 1 and y equal to 2. So in the second example, we don't have a feasible region. The goal is to create a feasible region. And how do we create a feasible region? We make use of the constraints. The constraints are inequalities, and we have 4 of them, and those 4 are right here. So constraints 1 and 2 simply tell us that the x value has to be greater than or equal to 0, y value has to be greater than or equal to 0. So if we combine those two, it simply tells us x and y must be in the first quadrant. So the possible values are right here, everything in the first quadrant. So that information we get from using the first 2 constraints. To go to the third constraint, we have 2x plus y less than or equal to 8. We can rewrite this as y less than or equal to 8 minus 2 times x, which if I rewrite it, I could write it as negative 2x plus 8. And that is of the slope-intercept form, y equals mx plus b. M here is minus 2, and the y-intercept is 8. So I'm going to draw that line now. So 8. And when I plug in x is equal to 4, I'm going to get 0. And it is going to be a solid line because we have less than or equal to. So that is the first constraint, or the third constraint. The fourth one is x plus y greater than or equal to 4, which would mean y is greater than or equal to 4 minus x. Before I get to that, let's look at the inequality in the third constraint. It has a less than or equal to sign, so I'm going to, didn't want that. So less than or equal to would mean all of those. Keep in mind, I'm simply trying to get to shape this properly. So that would be from the third constraint. And the last one when I rewrite it, I can rewrite it as minus x plus 4, which would imply the y-intercept is 4, and right there, it's going to become 0. And it is a solid line also. So I would have that, and since it's greater than or equal to, it would be everything above. When I combine all of them together, I would see that the feasible region is that part. And those would be the corner points. So we have 3 corner points, and that is the feasible region. The corner point here is 4, 0, 0, 4, and 0, 8. So we plug in the values x, y, and the objective function 3x plus 2y. Zero, 4, 0, 8, 4, 0. So we plug it in. 3 times 0 plus 2 times 4 equals 8. 3 times 0 plus 2 times 8 equals 16. 3 times 4 plus 2 times 0 equals 12. And the goal is to find the minimum and maximum value of the objective function. So the minimum value here is 8. The maximum is 16. So a minimum of 16 happens, of 8 occurs at x is equal to 0, y equals 4, and a maximum of 16 occurs at x is equal to 0 and y equals 8. So in example 3, we have an objective function which is 3x minus 2y, and we have 3 constraints: constraint 1, constraint 2, and constraint 3. The first one states that the value of x has to be between 1 and 5, including 1 and including 5. So constraint 1. Constraint 2 states that y has to be greater than or equal to 2. So those are all the possible values for the first constraint. Now I'm going to go on for constraint 2, which is y greater than or equal to 2. Now I needn't shade anywhere else because I know where the first constraint is satisfied, which is in the shaded area. So I'm just going to go ahead and shade where it is necessary, which is right over here. And the last case, constraint 3, states x minus y is greater than or equal to negative 3, which would mean negative y is greater than or equal to negative 3 negative x. Multiply by negative on both sides, y would be less than or equal to 3 plus x. which in slope-intercept form would be y less than or equal to x plus 3. The slope here is 1 and the y-intercept is 3. So that is the y-intercept, and I guess I'll plug in 2, get 5. Going to draw that line, so that would be constraint number 3, and it says y is less than or equal to x plus 3, so we're going to shade below the line. And keep in mind, we don't have to shade all over the xy plane, we just have to shade where things are satisfied in the first two constraints, and that would be right over here. So the feasible region is that part right there. So now we've got to know what these points are. Naturally, this is 5, 2. This point is, oh no. I'll just sketch the feasible region here. So that would be 2, 2. That is 2, 4. And that would be 5, 8. Now, if you can't figure this out, you can always go for the points of intersection between two lines. So we have a vertical line, which is x is equal to 2, and we have, oh, that should be 5. Goodness. It's right over there. So we could always plug the values in one of the inequalities to determine the points. For instance, if I plug in x is equal to 2 in that line, which is y equals x plus 3, I would get 5. And when I plug in x is equal to 5, I'd have 5 plus 3, I'll get 8. So in a similar manner, I can plug in or graphically see that those 2 points would be 2, 2 and 5, 2. So the corner points are 2, 2, 2, 5, 5, 2, and 5, 8. The objective function is 3x minus 2y. So I'm just going to plug in the values. 3 times 2 minus 2 times 2. 6 minus 4, we get 2. 3 times 2 minus 2 times 5. 6 minus 10, we get negative 4. 3 times 5 minus 2 times 2, we get 11. 3 times 5 minus 2 times 8, we get 15 minus 16, we get negative 1. So the smallest value is negative 4, so that would be the minimum. And the largest value is 11 in the objective function, so that would be the maximum. So maximum objective of 11 at x is equal to 5, y equals 2. Minimum objective of negative 4 at x is equal to 2 and y equals 5. So oftentimes linear programming, or 100% of the time, it is used in optimization, in the sense in business applications and in logistics and such. So we have to translate the practical application to a mathematical expression or a mathematical program for us to go for the objective in a particular application. So here is an example where a student earns $15 per hour for tutoring and 10 per hour as a teacher's aide per week. X would be the number of tutoring hours and Y is the number of hours as a teacher's aide per week. So we want to maximize the money the student is going to make. So the objective function Z would equal to $15 per 1 hour of tutoring, so times X, plus $10 per 1 hour of tutoring, so we have Y hours, so we have 10Y. And the student is subjected to the following constraints. So naturally, you have to guess that there are two constraints that are not specified here, which would be x greater than or equal to 0 and y greater than or equal to 0. The reason being time cannot be negative. X is the number of hours the student is going to work tutoring, and Y is the number of hours the student is going to work as a teacher's aide. So the other constraints that are specified here are that the student can work no more than 10 hours per week. In other words, when the number of hours the student spends in tutoring, when it is combined with the number of hours the student spends as a teacher's aide, that amount cannot exceed 10. In other words, x plus y has to be less than or equal to 10. And the tutoring center requires that the tutor spend at least 3 hours per week. In other words, the value of x has to be greater than or equal to 3. And lastly, the tutoring center requires that the tutor spends no more than 8 hours per week. In other words, we have x less than or equal to 8. So those are the set of constraints that the tutor has to work within. So first two, x greater than or equal to 0, y greater than or equal to 0, simply implies that the feasible region has to be in the first quadrant, which is right here. I'm going to go ahead and write the or draw the other constraints, which is x greater than or equal to 3 and x less than or equal to 8. So whatever feasible region is going to pop up, it's got to be between those two lines, because x has to be greater than or equal to 3 and it has to be less than or equal to 8. The next inequality is y less than or equal to 10 minus x. If I rewrite it in slope-intercept form, that's simply negative x plus 10. The intercept here would be 10, the y-intercept. Use a different color. and x is 10, then we get 0. Now, whatever value of y defined by that line, y equals negative x plus 10, has to be less than the line. So we are looking at that region, because that particular region is less than line, or less than or equal to be perfect. And I don't care about the second quadrant or any of the other quadrants, because we have to satisfy the first constraint, which states x has to be greater than or equal to 0, the second one y greater than or equal to 0, and x is greater than or equal to 3, x is less than or equal to 8. They all point to the region that I just shaded. The constraint for being between would be all of those values, and naturally the overlapping region is that, so that would be the feasible region. So what are the corner points? So that right there we know is 2, 0. That right there is 8, 0. And it seems like the two lines intersect at, or 3, 0, I'm sorry. Three, 7, and the last one would be 8, 2. Again, if you're not able to graphically see the corner points, you could always plug in x is equal to 3 in that equation, which is for the red line, negative x plus 10. You would see that the vertical line, x is equal to 3, intersects with the red line, y is equal to negative x plus 10 at 3, 7, and the same thing happens on the other side. At x is equal to 8, the vertical line x is equal to 8 intersects with the line in red, which is negative x plus 10 at 8, 2. So the corner points are 3, 0, 3, 7, 8, 0, 8, 2. The objective function that we have is 15x plus 10y. So we are going to plug in the values. So 15 times 3 plus 10 times 0, we have 45. 15 times 3 plus 10 times 7, 115. 15 times 8 plus 10 times 0, we have 120. And 15 times 8 plus 10 times 2, we have 140. So we want to maximize the amount of money the student's going to make, and that maximum value occurs right there. So the student, or we should say So how do we know if you have the right solution? Well, they have to satisfy the constraints that you started with. So x is 8, y is 3. Is x between 3 and 8, including 3 and 8? Yes. And when you combine x plus y, is it less than or equal to 10? Well, 2 plus 8 is less than or equal to 10. And is x greater than